One thing we always want to know in life is, does one thing cause something else? You know, does such and such cause cancer? Does doing this cause this to happen? And how do we go about showing that something causes something else? And whether they're just associated, but one doesn't actually cause the other. We talked about association in the first unit when we were talking about categorical data. So like, you know, if we had an example where the number of students taking AP statistics has increased over the last 10 years. The number of students who, I don't know, number of students who what? Give me an example. Something ridiculous. The number of students that die by choking on their bed sheets, getting tangled in their bed sheets, choking to death, has also increased in recent years. Okay, does that mean that one causes the other? Not necessarily. Okay, are they associated? Yes, as one goes up, the other goes up. Sorry, I couldn't. There was an example of that in a textbook I read. That was the only example I could think of. It's not like I have a morbid thought process. Anyway, but we can pretty safely say that, oh yeah, if you take AP stats, then your risk of death goes up. Okay, that doesn't make sense at all. So when can we say something causes something else to happen? Well, it depends on how we go about testing, right? And so we're going to talk about observational studies versus experiments in this lesson. So as an example, you see a segmented bar graph here with 5 bars that shows the historical comparison of gender in scientific careers across countries and disciplines. So these, the first 4 measured the percent of papers written according to a certain discipline by males and by females. Okay? And I assume that these are published articles. So for all science papers, of all the science papers published, nearly 2/3 were by men. And then slightly more than 1/3 were by women. It gets worse when we go to engineering papers that have been published. It gets even worse when we go to physics. It gets slightly worse when we go to mathematics. And this last one talks about the percent of people in the data science workforce. You can see that 85% are male, 15% are female. Okay. So what explains this? Well, one possible cause of gender gaps is something called hiring bias. So how do you think hiring bias would cause the trends that you see in the segmented bar graph? Who's the hiring bias against? Women, right? Okay. So we could say that hiring bias against women would cause less to be working And what do we call all these disciplines all together? What's that name we give? STEM. So science, so basically this covers science, technology, engineering, and mathematics. Okay? So using this observational data, and this is called observational data because it was just sort of looked at and collected. Okay, nothing was manipulated, nothing was tested, this information was just gathered. Okay. Can we prove that hiring discrimination is the cause of gender bias or gender gaps in scientific careers? Just by looking at this and saying, well, looks like there's hiring bias against women in STEM fields. Okay. No, we can't say for sure. No, not for sure. Maybe, but perhaps there is something else besides hiring bias. That explains the gap. And that's something else we would refer to as a confounding variable. So confounding variables, they provide alternate explanations for something. Between some explanatory variable and some response variable. In this case, gender, and for response, hiring rates. Perhaps something else is at play here. Can you think of anything else? Could you think of a confounding variable besides just hiring bias? Yep.
Education, like, yeah. Same as the hiring gap at the university.
Yeah, like, yeah, you're right. And because there's still sort of this mythical belief out there that men do STEM fields, women don't. Okay. Or they're, you know, and it's a very outdated belief, and it should have never existed in the first place. Okay. But it's there. So one confounding variable could be like traditionally men have been pushed, encouraged to go into STEM fields. Where women have not, or where women are actually, never mind not, where women have been discouraged. Right? Okay, so what was done here to try and prove cause and effect was an observational study. Okay. So an observational study is a study in which data is collected without any kind of treatment. It's just there. The information's there. You just collect it. Okay? Or you create the information yourself by keeping track. So a retrospective study examines existing data. That's what that was what was done above. A retrospective observational study. Just used observational data, how many papers were published by men in this field and that field, how many men are in the data science workforce as opposed to women. A prospective study follows individuals to gather future data. I don't know if you've ever heard of studies where they'll follow children all the way up to adulthood from when they're babies because they want to measure something. So it will be like an observational study that is like 18 years long before they can publish anything. They did, I think they did that in Manitoba one time. They looked at students starting in grade 6 to grade 12, so it wasn't as long. Okay? But that's a 6-year study. Okay? And you can get some interesting information out of it. Okay? However, the problem is, while you can see associations and you might be able to apply it to certain populations, observational studies, regardless of whether it's retrospective or prospective, do not show cause and effect. Okay, this is very important. If we want to get to something causing something else, we have to go to an experiment. Okay? And what do we do in an experiment? Well, an experiment is which there's some sort of treatment is imposed on subjects. And those subjects could be here, you might as well take this.
Oh, thank you.
Yeah, could I get you candy or anything? You okay? Could I get you candy or anything?
No, I already spoke.
You're okay? Okay. Anything else you need?
I'm so sorry.
Hey, you always say you're sorry. Like I say I'm sorry as I elbow my way through a group of people. Oh, sorry. Oh, sorry. Sorry. Yeah, don't close it. Just leave it open. Okay. Okay. Good. I wonder how these video lessons actually sound. Okay, so an experiment is a study in which treatment is imposed on subjects. Subjects could be people, they could be animals, they could be inanimate objects, okay? And if they are well designed, we will talk about what makes up a well-designed experiment, okay? They, let me get the wording right here, can show cause and effect by controlling confounding variables. Okay. So it tries to focus on, does this specific explanatory variable cause this response? Okay. And we can control for that and prevent any confounding variables from entering into the picture. Okay, so here is an experiment. It's called the study, but it's actually an experiment. So in this study, experimenters printed up copies of fake application materials for a science lab manager job. The applications were completely identical except for one name. Half the applications it said John, the other half it said Jeff. Okay, so everything else was the same. And so they found 120 science lab faculty members. They randomly sent them either a John or a Jennifer application. One more Jennifer application, doesn't make a big deal. Each faculty member was told that the application was actually for a real position at their university. And so the faculty members were asked to rate the applicant's hireability on a scale from 1 to 7 and estimate what their starting salary would be. Okay? Some terminology you need to be familiar with. The experimental units are the individuals or subjects that are assigned to the different treatments. Who were the experimental units in this study? Sorry? Not Jennifer and John,
The people who received
the faculty members. They were given the treatment. It's like who or what is given the treatment are referred to as the experimental units. We've talked about this before. The explanatory variable is the variable that is purposely manipulated or controlled. Okay? With the value assigned is manipulated. Another name it's known by is called the factor. Okay? What was the explanatory variable in this study? The name. Jennifer or John. The treatments are the different levels of the explanatory variable in the experiment. Okay? What were the treatments in the study? What was the treatment that was imposed on the experimental units? What were they given? What were they given? Yeah, they were given resumes. Okay. Resumes for the treatments. And finally, the response variable is the measured experiment outcome. That's compared between the treatment groups. And what would the response variable? There's actually two of them in this case. Hireability and salary. Okay, so those are different terms you should be familiar with when we talk about experiments. Now, when we actually do an experiment, there's 4 main components that lead to a really good experiment in which we can say with confidence that something causes something else. And these are the 4 components. First of all, comparison. Okay? You want to be able to have 2 or more groups to compare. So how is comparison used in the Jennifer John study? Yeah, we had two groups, didn't we? We had two, I won't call them control groups, but two groups that received the treatment. Okay. So two groups. Received the treatment. And compare hireability and salary. And then you just see a note here that in many experiments, often we're determining the effectiveness of something, such as a new drug. Okay, so we would do what's called a comparative experiment when we have two groups. One group actually receives a treatment, the other group will likely receive nothing at all or an alternate treatment. Okay. In this case, in this experiment, both groups were treated with something. Okay. Because it only makes sense to do that in this experiment. Second component that's really important, okay, random assignment. So why would it be a problem? Say, for example, if the experimenters said, okay, we're going to take this highly rated university and give them all the John resumes, and we're going to take this well-rated university and give them all the Jennifer resumes without randomly assigning. What's the potential problem in that? What's that? The universities do?
Like, there's like different sets of people, like, kind of the same environment.
Yeah, like wouldn't that introduce confounding? Because how do we know, like, you know, you're given all this, one would consider that the people at the top tier university have a better reputation. Okay, and if they're all given the John, perhaps that's going to favor John, when maybe if we would have done it randomly and just said, okay, we're going to randomly give the top tier half John, half Jennifer, and that second tier half John, half Jennifer, and then we're going to compare the results after that. One would think that would give us a better result or a more accurate result if we did that. Okay. So this, if you get this, would create confounding. Okay. It's gender or university quality. The cause of whatever outcome we get. So all of a sudden it's like, well, how do we know this is because of gender? So that's why we want to do it randomly. Okay? Because randomly, and this is probably the best explanation for why random assignment is so good. And let's say we're comparing two groups. It creates two roughly equivalent groups. character-wise and character trait-wise. Okay?
So it creates two roughly equivalent groups.
Which is going to reduce confounding. Okay?
So cause and effect conclusions could be made.
I mean, and again, I mean, that's really, it's kind of a way to say control. Something to remember between sampling and experiments.
Random sampling, we talked about this earlier in the unit, produces bias.
Okay?
Random assigning in an experiment, random assigning to groups, reduces confounding.
So that's the second factor. Third factor is replication, and it's not what you may think. It does not mean doing the study or the experiment over and over again. Okay?
Replication means having many subjects.
Or individuals in each treatment group. Okay? The more the better, within reason. Obviously, there reaches a point where a certain number is just too many to deal with. It becomes too cumbersome.
Okay? So, as an example here, two questions.
Would it be a problem if I only assigned one faculty member to the John group, one to the Jennifer group? Why would it be a problem? I think we all agree it would be, but why? What's that?
Wait. You need assignment and
Like if we just said, okay, one, like, and we could randomly assign them too, doesn't matter. But why would, like, having only one to each group not be very good?
The group?
Like the amount of faculty members.
Yes, you're right. It's not large enough, but what could that cause? Like what's now become, if we only do one in each group, what's now the focus?
their personal basically dictates the entire experiment.
Exactly. Okay. Now all of a sudden it's coming down to, we're not creating two roughly equivalent groups. It just comes down to who got into, or who got assigned to which group by chance. Okay.
Which is obviously not good experimental design. So it would be difficult to tell if differences in learning were due to gender discrimination, which is what we're studying here, or chance variation between two faculty members. Yeah, it comes down to their personal views. And this leads to the second answer to this, or the answer to this second question. Why is it important to include many experimental units in each treatment group? Because larger groups reduce the likelihood of differences caused by chance. Caused by chance. Finally, control, which is kind of, we've really been talking about this the whole time. Okay? Like we want to control for confounding. That's what we want. So we can isolate, does this explanatory variable cause this or not? Okay. So how was control used in this study? It is. How did they control it? If you look at the original paragraph, what did they do?
The entire resume is the exact same.
That was probably the biggest one that's second. Resumes were exactly the same except for the name. Okay.
I mean, who knows, maybe other things were controlled as well. You know, they were given the resumes or asked to rank them at the same times of day. You know, because different parts in the day, maybe you're tired. Okay, and you want to get things over with. So they're trying, I'm sure they spent a lot of time trying to account for and control certain things that could cause confounding. So out of all of this, we get what's called a completely randomized design. So that's an experimental design in which the experimental units are assigned to treatments completely at random. How do you describe a completely randomized design? Well, there's a couple ways you could do it, actually. One is you could use a diagram. The other is you could just write a paragraph. So, and then this shows you down here what you should be following when you describe a completely randomized design experiment. Okay? So I'll just do a paragraph. Assign each faculty member a number from 1 to 127, because that's how many were in the group. Go from 1 to 127. Randomly generates what was it? Generates for 63 different numbers. And assign these people to the genre. Maybe go to the gym.
Okay, apply the treatments or give them the resumes. In this case, give resumes. And record hireability ratings and salary. Should always add this in at the end. Compare the results. So that's how you would do it. Okay. Or like I said, you could have done almost like a flow chart in a way. That also works as well, but this is pretty easy to write out. Okay. And I'm going to leave it there. If you want to look at the discussion, I'll let you do it on your own.